Hello. Today I'm going to take you into the magical world that is electrochemistry. Electrochemical cells are all around us, even though we might not realize it. Whether it's in calculators, cameras, cell phones, laptops, power tools, or even in cars, electrochemical cells are interwoven into our lives. Now, you might be asking yourself, what's an electrochemical cell? Basically, it's just something that harnesses the power of chemistry by transforming chemical bonds into electricity. Now, let's let Professor Emeritus Robert Huggins from Stanford University give us a brief history of modern cells.
People at Ford Motor Company had discovered that you can make a very interesting battery out of sodium and sulfur using a solid electrolyte. Sodium sulfur was a very different way of looking at batteries. Up until that time, most of the batteries people were working on and were interested in had water as the electrolyte. Sodium sulfur with a solid electrolyte was a real revolution. The next real breakthrough in batteries was the discovery that you can make a room temperature lithium battery. And the key element of that was some work done in Oxford University, which they discovered you can use a material like lithium cobalt oxide as an electrode in a room temperature lithium battery. But these room temperature batteries didn't use molten salts, they used organic liquids. The next breakthrough in the battery technology was the recognition by Sony in Japan that you could make a very interesting battery if you use this lithium cobalt oxide that people in Oxford had discovered, but also use graphite on the negative electrode side. They realized you could take this graphite work and the lithium cobalt oxide work and put the two together and make a rechargeable battery. The science community tended to look at different parts of this, but Sony was clever and they saw they could put the parts together. And so that was really the beginning of modern lithium batteries. The technology has really moved ahead, but there hasn't been a really significant change since then.
Now that we have a bit of a better background, let's see how it's being implemented today at Palo Alto startup Tesla Motors.
So we work with all the major lithium-ion battery suppliers, the main ones being in Japan and Korea. And for us, what we're trying to get them to do is come up with a modified cell that's automotive grade, specific to EV applications. So we're taking an existing form factor, an existing chemistry, and we're modifying it to get one that is balanced properly. It takes a lot of optimization. And that's something we work very closely with our suppliers on, to get cells that have a very high energy density, that have a good cycle life, good storage life, low impedance, but the most important thing is a low cost. So we look at all those kind of characteristics and try and get a nice balance. The technologies they're looking at are really varied. Lithium air is a big one, sodium sulfur. There's some different technology. There's some solid state technologies as well that different groups are looking at. So there's a wide variety of different chemistries. Now, which one of these is going to win is a very good question. It's hard to predict now which one will, but we've kind of got our odds on a few of them.
There are two directions that people think would be really wonderful. And one is to make a lithium air battery. The second rank is lithium sulfur batteries. And you can calculate you can get a lot of energy from a combination of lithium and sulfur, but the problem is nobody knows how to make it rechargeable. And the difficulty there is that the oxygen electrode is not reversible. And so there's a lot of work going on in laboratories all over the world trying to figure out how to solve that problem.
The research that I'm doing is trying to get sulfur materials to work in lithium-ion batteries. And the reason that we're exploring that, there are basically three reasons, I would say. The first and sort of most important reason is that if based on theoretical calculations, if you use sulfur instead of the materials that are used right now in lithium batteries, you should be able to store up to 5 times the amount of energy for the same amount of weight. The next biggest one I would say is cost. Some of the materials that are used right now use cobalt, nickel, materials that are a bit more expensive, and if you ask most of the people who are doing research on trying to implement batteries into electric vehicles or other systems where they require a large scale, a lot of material usage, they'll say cost is the #1 factor that is preventing them from really taking off. And so sulfur is a very abundant, very cheap material. And the third big one would be safety. So some of the materials that are used now have some elements of toxicity to them, and there are reasons to believe that sulfur could present less hazards than those materials. So that's the reason that we're doing sulfur, and everything I've described so far sounds great, like why don't we have this already? Well, there are also a lot of other problems, and the two main ones with sulfur are, one is that it's an insulating material. It's not electronically or ionically conductive. And in a battery, you need to have both. You need to be able to move the electrons through the material, and you need to be able to move the lithium ions through the material. And sulfur doesn't do either of those very well. And the other main obstacle is the cycle life. So you can get a lot of energy on the first cycle, and the second cycle significantly less, and the third significantly less than that. And the major reason we believe for that is that the sulfur tends to dissolve in some of the liquid electrolyte components that are in almost all of the batteries that people use. They have a liquid electrolyte, and so the sulfur dissolves a little bit in that. And so every time you use it, more and more dissolves, and you lose access to that material. One approach that we have done is to use nanostructured material, which is called a mesoporous carbon. And what that means is we use carbon, sort of like graphite, and it's sort of engineered on the nanoscale to contain very small pores, about 3 nanometers, that we can actually put the sulfur into these pores. And so because the carbon is conductive, now the electrons only have a very small pathway in the sulfur that they can get to. So even though sulfur is not conductive, the distance the electrons have to travel is so small that we can actually run the material at much higher rates. This is where most of the battery work that we do gets done, is in this room here. What you can see over here is mixing slurries of different battery electrodes. And so the reason most of them look black is it's a mixture of whatever your active material is, whether it's silicon, sulfur, lithium iron phosphate, different materials, mixed in with carbon and a polymer binder. If you're making a coin cell, what you might see in like a watch battery, we use this big guy over here, which presses it all together. And then there's just also a lot of different chemicals in there to do different things that you're able to do inside an air-free environment that you can't do outside. Some of the new electrolytes that I've been developing have shown significant improvements in being able to retain the sulfur and not lose it. But then there are other complexities that come with having that, and so that's generally what I'm working on now. I've been able to use this electrolyte and reduce the amount of sulfur that gets lost and dissolves, but now some parts of the system run slower, so it's harder to extract the energy as quickly, and so I'm looking at different ways to attack that problem.
I don't think it's ever going to happen. But, you know, that's the kind of prediction that you always turn out to be wrong. I wouldn't work on it, because somebody's got to come up with a very different approach to lithium air or lithium sulfur than what's being done now. And I don't see that yet.
You know, theoretically, we should be able to get all of this energy out of it, but there's a lot of really large hurdles that come in. So with lithium air, a lot of the problems are actually quite similar to lithium sulfur, but sort of with an added higher level of complexity to them. It's a very complicated system. the payoff, if you can get it to work, is tremendous, and I definitely think it's worth putting in a lot of resources and to do the research on that.
There are some significant technical challenges to enabling the commercialization of it, starting with cycle life. Another issue is the power. I mean, you need to get enough power from these batteries to drive up a hill at 70 miles an hour. So I would imagine that the first implementation of a metal air battery pack would be some kind of a hybrid, where the metal air is providing some longer term storage on board the vehicle. But it's many years away, I think, until the metal air chemistry is actually commercialized. There's a wide variety of different chemistries. Now, which one of these is going to win is a very good question that we spend a lot of time talking to the developers to try and get a better feel for that. We go to the battery conferences to try and get a good handle of it. But at this point, for us, we're trying to establish contact with as many of these firms as possible and trying to evaluate their technology and figure out which one is going to succeed. It's hard to predict now which one will, but we've kind of got our odds on a few of them.
Well, the real challenge is to get something that's going to give you the amount of energy you want, at the price you want, and the cycle life you want, and the safety that you want. And for different applications, the ratio, the significance of these different parameters shifts.
There's different research being done, and I think it's important to tailor the research to what the application is. There's a lot of talk about using lithium batteries for grid storage, and personally that doesn't make a lot of sense to me, because the advantages for lithium batteries is that you can store a lot of energy in a small space and it's lightweight. But neither of those really matter if you're talking about huge scale, utility scale grid storage and cost too. I think that especially in sort of an academic environment, cost is overlooked a lot of the time because it's not something that you deal with on a day-to-day basis here on a lab scale. But if you're a company and you're thinking about using these things, then that's really important.
Well, it's definitely going EV. EVs are gradually taking off by the year 2020, and could be 5% or 10% of the number of vehicles, which would be phenomenal if that actually did occur. But it'll keep growing from there. I really think as battery technology gets better, EVs, the percent of commercial vehicles that are EV, and it's going to be just increasing year after year. Batteries are based on chemistry. And so they're not electric components, so we're not subject to Moore's law. Unfortunately, our pace of invention is much slower in batteries. So you may get an 18-month doubling of productivity or speed out of chips or other electronic devices. But for batteries, it's very different because it's chemistry based, and generally it's a 10-year cycle. So every 10 years you get a doubling of energy density. It's a very different world, the electronics world. There's more and more research money going into batteries, fortunately. I mean, 5 years ago, it really was not a exciting industry like it is now. But now with all the focus on alternative transportation,
I think it's definitely important to continue to look into a lot of different solutions at once and not think that we can pick a winner at this point, but to develop batteries, develop fuel cells, develop biofuels. And like I mentioned before, I really think that cost is going to be the key to determine what the winning technology is. But it can also be a combination of technologies. You can have a fuel cell car, you're still going to need a battery on board. You can have like a biofuel hybrid with a good battery, things like that. So there's definitely room for the technologies to come together as opposed to just compete against each other.